This is example problem 469 from your book. A structural steel bar of rectangular cross-section consists of uniform and tapered sections as shown in the figure. The width of the tapered section varies linearly from 2 inches at the bottom to 5 inches at the top. The bar has a constant thickness of 0.5 inches. Determine the elongation of the bar resulting from application of the load. Neglect the weight of the bar. So first let's find E for steel from the table in the back of our book. That would be 29,000 KSI. Now, because we have this cross-section that has a varying width, the cross-section looks like a rectangle because it's a bar, but this is T, they gave us is 0.5 inches, but this width here is going to vary from 2 inches at the bottom to 5 inches at the top. So we need to figure out how we can describe that as an equation. So what we need to do is actually think of it more like this and write an equation of a line. So we're basically going to write an equation of a line, of this line right here. And we're going to do that. So if you think about it like this, and the reason that we need to think of it this way is because when you describe the equation of a line, you want the independent variable here and the dependent variable here. So the independent variable is going to be the length that we're going, and then the independent variable, or the dependent variable, is the width. The width is varying and is dependent upon the length. So if we think about this, we start at 2 inches here for our width, and we end up at 5 inches here. So we have a line from 2 to 5, and here this is 60 inches, and this would be 0. So now we can just describe this line. So we have y equals mx, mx plus b. So we can describe the slope of this line is equal to the y, so we have 5 minus 2 over the x, 60 minus 0. So our slope is 3 over 60. So we have an equation y equals 3 over 60 times x plus 2 inches, because we have our intercept is 2 inches. So now we have a line, or an equation, that describes how our width varies with our length. So now we can do our deformation. So our deformation is the total deformation is equal to reminder, PL over AE. But if any of these are changing over the cross section, we have to integrate. But we can talk about this bottom section first. This section has no changes. So let's just put that one in there. We have our force of 30,000 pounds times the length of that section, which is 25 inches, over the area of that cross section, which would be 2 times 0.05 inches, times the E that we found, 29 times 10 to the 6th. So that's for just this part of the member. Now we have to do the second part, which we have to do some integration. But we know that our force is constant across that cross-section. So we're going to leave it out of the integral. So 30 times 10 to the third pounds we have. And also our E is constant, so we're going to leave that out of the integral. KSI, or PSI, sorry. So leave that out of the integral, and then we integrate from 0 to 60 over the entire length, so from 0 to L, that equation that we just derived. But that's only the width. We derived the equation for the width, but the area is actually the width times the thickness. So we have, and it's on the bottom of our equation, if you remember here, PL over AE. So we have our equation 2 plus 3x over 60. And then we have to multiply it by our thickness, 0.5, and we're integrating over the length, dx. So we're calling this our x direction. So from that, we get that our total deformation is equal to 0.02586 plus 1.03448 times 10 to the minus third times 40 times the natural log of 40 plus y from 0 to 60. So our overall deformation is equal to 0.0638 inches.